Intel QLC, cost-effective Ceph on NVMe. Legal disclaimers. First slide, SSD versus HDD, the reality. I'd like to use SSDs for Ceph OSDs, but they can't compete with HDDs. SSDs are too expensive, SSDs are too small. QLC technology is too slow, and the drive rates per day are too low. HDDs are more reliable. These are definitely now myths. Start with cost. TLC or excuse me, still getting my throat up in the morning. QLC, TCO over crossover soon or today. They're competitive now, especially if you consider some subtle factors that some of the online TCO calculators don't include, like the impact on your service, how well your service can run with HDDs. Some people short stroke HDDs or limit the size of the HDDs that they'll use because of the interface bottlenecks and the recovery times that they experience with the HDDs. Oftentimes one sees HDD deployments running out of IOPS long before they run out of capacity, and people will deploy extra drives in order to approach their IOPS needs. And I've even seen people with HDD clusters who have data coming in faster than they feel that they can safely expand them. Other costs include terabytes per chassis, terabytes per RU, terabytes per watt, the operational expense of swapping drives, of having to RMA and crush them. A lot of operations, for example, won't bother RMAing something worth under $500 because of all of the hassle and effort. Some places it costs that much just to get somebody through the door if it's off in an off-site. SSDs allow you to do cluster maintenance without prolonged and reduced redundancy. If you have a failure and it takes you a week to recover, then that's a big window of risk for additional failures. And then, the less quantifiable, how much does the degraded user and customer experience cost, especially during recovery or when you have an incident? Capacity. Today's QLC SSDs enable you to deploy with fewer chassis and fewer RUs and fewer racks, all of which can be quite expensive. 144-layer QLC NAND enables high-capacity devices. Intel's NVMe QLC SSDs are available capacities up to 30 terabytes. And you can fit up to 1.5 petabytes raw space per rack unit with the Ruler E1.L EDSFF drives. That, having come from a time, cough, cough, when my first hard drive was a 5 megabyte, 14 meg pack, that just blows me away, the density that we can get today. And the abundance of IOPS that SSDs give you allows flexible capacity provisioning where you don't have to provision for IOPS anymore. You can provision for your capacity. Performance. SSDs, including QLC, are fast and wide. Intel SSD D5 P305316 NVMe QLC delivers up to 800K 4K random read IOPS, a 38% increase over the previous generation. Up to 7,000 megabytes per second sequential read, more than double of an improvement over Intel's previous generation QLC. The SATA drive saturated about 550 megabytes per second. And the PCI Gen 4 NVMe interface crushes the SATA bottleneck. 2 or more OSDs per device improve throughput IOPS and tail latency. This is common practice with NVMe drives, the NVMe interface allows you to do that and work around some of the serializations in the code and so forth.
Anthony,
Operational.
just one really quick question. Are you presenting on the other screen possibly? Because we're seeing, yeah, okay. Now we're seeing your update. I think maybe the BlueJeans is just updating more slowly. That might be it.
Okay, are you seeing the operational advantages slide now?
Yeah, no, I'm seeing it now. Yeah.
Okay.
Sorry, go ahead.
No, I only have one screen now. Operational advantages. The RGW service for Ceph object storage, for example, is prone to hotspots and QoS events. One strategy to mitigate latency and IOPS bottlenecks are to limit the size of HDDs used, for example, to 8 terabytes. Other things that one can do are to limit scrub intervals, put a CDN on the front end, throttle or cache on the load balancers in front of multiple RGWs. But sometimes OSD upweighting, especially when using EC on HDDs, may still take weeks when it's done so gradually as to not impact user service. Even OSD crashes can impact API availability. And the whole reason we use Ceph is, for continuity of service. Replacing HDDs with Intel QLC SSDs for bucket data can markedly improve your QoS and serviceability of your clusters. Reliability and endurance. QLC reliability is better than you think, and it's actually more than you need. It turns out most SSD failures are firmware, and thus you can fix them on the drive. Which in my experience is not as true with HDDs. Studies show that 99% of SSDs never actually exceed 15% of their rated endurance, which was a bit of an eye-opener, having come from an assumption that you needed one theoretical drive write per day to do RBD, for example. The RGW service, in one case has been calculated for 7 years of endurance using the previous generation QLC. The new drives would be even better. Reliable endurance, get with the program, erase cycle. That's a NAND joke. Everybody giggle. The 30 terabyte Intel SSD D5P5316 QLC SSD, much like the Illudium Q38 space modulator, is rated at over 22 petabytes of IU-aligned random writes. One drive write per day, 7.68 terabyte TLC SSD, is rated at less than 15 petabytes of 4K random writes. Something that is not often known is that with many SSDs, you can actually tune endurance via over-provisioning. You can adjust the amount of reserve space that the drive has, which can extend your reliability considerably if you need to adjust it. Reliability and OpEx. Drive failures cost money and quality of service. I've run Ceph clusters where a drive failure sets off escalations, and the fewer times any of us have to be awakened at 4 a.m, the better. 8 terabyte HDDs have 0.44% annual failure rate spec, but turn out to be on average 1 to 2% actual failure rate in production. Intel's DC QLC NAND SSDs in practice have an average failure rate of less than 0.44%. They have a greater operating temperature range, better Uber error rate, and consider the cost to have hands replace the failed drive. I've been in situations where it was $400 just to get somebody through the door. Intel QLC SSDs deliver up to 104 petabytes written, significantly outperforming HDDs. Here are some figures comparing, publicly available figures comparing a couple of hard drive models. In the middle, a TLC SSD model, and then QLC SSDs with random and sequential writes, and with a figure showing additional over provisioning. This shows at just how much improvement you can get in endurance by adjusting your over provisioning. Optimize endurance and performance with these Course IU QLC SSDs. It is beneficial to align the BlueStar min alloc size to the IU size, the indirect unit size of the drive. 64K for the new drives, 16K for the drives that are already out in the field. Writes aligned to IU boundaries on multiples enhance performance and endurance. And simply aligning with BlueStar min alloc size may not, very well align your metadata, but it turns out to be a small percentage of the overall workload, and that doesn't have a large impact on the drives and durability because the drives are so big. Some example use cases: RGW, large objects, RBD when used for backup, archive, and media. I've experienced RBD used those ways. Ceph has a 4 megabyte block size, and it seems as though QLC could be a good fit for Ceph. That's testing we still need to do. Next slide. Additional optimizations. There are more things that we're exploring. Aligning the RocksDB block size to the IU size, and exploring RocksDB universal compaction. I believe neither of those is by default, and they should give us better performance and better write amplification at the expense of using a bit more space. But again, when you have 30 terabytes, maybe that's a good trade-off. Other RocksDB tuning may be beneficial. Another route is to use Optane to accelerate WallenDB on a separate device, or engage in other write shaping activities. Crimson, may bring us, some optimizations for Course IU drives as well. And for RGW, we're looking at separate pools for large and small objects. With EC and especially with raising the BlueStar min alloc size back up, RGW's fit for small objects isn't great, and you can have a bunch of stranded space. And so, I talked to the folks on the RGW refactoring call a couple weeks ago about perhaps using Lua scripts to adjust storage classes and have multiple pools. There's talk of there being scaffolding within RGW to have multiple pools for behind the scenes more transparently. And so those are some additional things that we can look for in the future. And here's a bunch of all of the references. PowerPoint really, really likes to make these gray. I'm still learning PowerPoint. And that's the end of the story. Any questions?
I have some questions. Towards the beginning of the talk, you mentioned the new ruler form factor SSDs that let you fit 1.5 petabytes in a rack unit. blows my mind too. Are those ZNS devices? And or
No, no,
is Intel planning to ship
I'm,
ZNS soon, or
I'm
what's the ZNS story here, I guess?
you're young. Maybe you can chime in there. These are not ZNS. I think ZNS. I'm not sure if we're shipping ZNS yet. Um, those are the long format roller drives, the 30 terabytes, and Supermicro offers, in this fine print that you can't read, Supermicro offers a system that gets you around 1.4 terabyte, 1 terabyte raw, and somebody else that I found offers a system that has additional roller drive slots on the back. And so, it's a fairly deep chassis because you have these long drive bays on the front and the back. But as I calculate, it's a 2-year system that can take, it can take 108 drives, I think. And so, if you do the math modulo base 2, base 10 rounding, that gets you somewhere in the neighborhood of 3 terabytes raw space in 2U, divided by 2, 1.5 per RU. I've
So,
been in situations where I had to fight tooth and nail to get a single rack unit. Literally a pop that was in a closet in Sofia, Bulgaria, for example. So I'm very focused on minimizing rack units.
so can you hear me?
Yes.
Oh, okay. Yeah, I was sorry. I had some technical issues at the beginning. First is the audio, now is the microphone. But so this is Yu Yang. Hi, Sage. So yes, no, this is not a ZNS device. This QLC drive is just that Anthony introduced today is block device only, but it's using the coarse indirection, meaning that it's optimized for larger block size than the traditional 4K. So the ZNS is, most of the vendors is under development at this moment. I don't think there's a product that's already being available to the broad market yet.
Is the plan though to offer these devices with the ZNS interface
Yeah,
firmware?
definitely. We do have a plan to offer ZNS feature in the future with a ruler form factor.
Cool. Okay. Okay. Thanks. A couple slides after that, you mentioned over provisioning to balance against durability versus capacity. Is that like an explicit management operation that you have to instruct the device to do that, or is it just a matter of writing to a constrained set of LBAs in order to avoid that trade-off?
I've been wondering for years if it matters which way you do it. Some people do effectively short stroke it just from the user side, but you can also use the usual tools, including Intel MOS tool, to just direct the drive to report itself at a smaller size.
Okay.
Now that I work with experts, I want to look into that to see if it makes a difference which way you do it.
Yeah, you should go
Certainly,
figure that out and report back. I imagine lots of users would be very curious to know. I mean, I suspect it depends on the firmware, how the firmware behaves. It will vary device to device, but at least if we have a vendor answer.
certainly not filling the drive. Wear leveling. Is going to have a similar effect. But I would definitely look into that. I know exactly who I want to ask.
Cool. A couple slides after this, you were talking about reliability, and you mentioned the 0.44% AFR for SSDs. But earlier you had mentioned that usually when SSDs fail, it's like a firmware fix and not like an RMA hardware failure.
Mm-hmm.
Is that AFR? Is that firmware errors, or is that like not
Tell you the
inclusive of
truth,
that?
I'm not sure.
I can take this.
Yeah.
So the AFR target for SSD include all the failures, not only firmware. Although firmware may take the majority of it, there's also, hardware failure and also, different kind of failures for SSD. Usually for Intel's NAND SSD, we have an annual failure rate target of less than 0.44%, where most of the time we are able to beat this target. In our QLC NAND example, we are way below this 0.44 target. And the reason is, so QLC NAND right now is, and Intel is the only one that's using a floating gate technology for QLC NAND. And as far as I know, nobody else is using floating gate SSD technology nowadays. So this floating gate technology is really good for having large capacity NAND components, as well as have really fast NAND components, and also reliable NAND component that's have a really good retention rate of their data. So that's why Intel's QLC SSD has a really low annual failure rate, which is quite different from what the market think. Usually, when they think about QLC, they think about the quality is lower than TLC, which is not true at all.
What's floating gate?
Oh, floating gate is a kind of technology that we make this NAND component. Another technology that is different than floating gate is charge trap. So it just, floating gates means you have two gates in each NAND cell, and you use that floating gate to store the 0 and 1s of the data.
Okay, and then I guess the last question was you had a slide where we were talking about the IU and the block size.
Yes.
Yep. I guess maybe it's just one more. The question was there we go. Is the IU something that is exposed in the kernel block device properties and SysFS or wherever it is, so you can tell what the preferred write unit size is? Like, is this something that we can make BlueStore automatically detect of the device so that it automatically sets BlueStore min-alloc size accordingly, or is it
Yes.
something that you have to know?
Yeah, the answer is yes. I can't remember the the thing that you have to read, but definitely it is reflected.
Okay. In that case, a pull request that makes BlueStore do that during makeFS would be extremely welcome, because at the end of the day, we don't want users to have to know any of this, right? We want them to just be able to plug in this device and have it use an appropriate allocation.
On the other hand, they also don't want rude awakenings if they're writing a bunch of small objects.
Yeah, but they probably don't. I mean, they should be writing. I don't know. Yeah, somehow we want to know.
Well, I've seen people, using object storage to mirror their Git repositories, but then, also to store, TV shows dubbed into Portuguese.
Right.
So a lot of it depends on your workload.
Yeah.
I will certainly work on. That's a very good idea, automatically setting that, and I'll talk to our internal folks who are working on BlueStore about that.
Yeah, I mean, maybe a tunable that controls whether you automatically align the allocation size.
Of course. I'll always give somebody the option.
Or even like a health warning or something if this allocation size is low. I don't know exactly how we'd want to do it, but providing visibility here so that, and ideally some default behavior that's same would be great.
Yeah, that's a terrific idea.
And the one other thing I'd mention here is that I mean, you call out that the RocksDB workload is a pretty small fraction of this, which is true, but there's also a BlueFS allocation size tunable that could be set. So we could also tell BlueFS to respect a larger block size as well.
Yeah, I actually asked one of our internal folks who was described to me as a BlueStore expert, who works on that. I think he's in the PRC, and he thought that it wouldn't make a difference for the BlueFS alloc size. And so, in the absence of more information, I have to defer to the guy who wrote the code.
Yeah. Okay. Cool. Okay. Thanks. So those are the questions I had.
Thank you, sir. Anybody else? We can call it whenever you're ready, Mike, then.
Yeah, just giving people a moment. Okay. All right. Well, thank you, Anthony and Yuan, for
As
giving
everybody
us
fumbles to unmute. Alrighty.
All right. Well, thank you for the presentation. And thank you, everybody, for joining us for our final day for week 2 for Ceph month. And be sure to join us for week 3. And recordings for these will be posted up on the Ceph YouTube channel today as well. Thank you, everybody, and have a good morning, good evening, wherever you're at. Thank you.
Thank you very much.